Hi, my name is Alex Botros. I'm one of the authors on this paper, and today we'll be discussing our approach to learning a control set for use in lattice planning that takes into account the preferences of the user. Now, the high-level goal of this paper is to design a motion planning scheme that takes into account user preferences. We use lattice-based motion planning, so the configuration space of a mobile robot is discretized into a regularly repeating grid called the lattice, and vertices in this lattice are connected via pre-computed feasible motions for the mobile robot called a motion primitive. This is a very attractive approach because the complexities inherent to the system and the system dynamics can all be taken into account offline during the motion primitive computation phase. Also, the regularity of the lattice facilitates theoretical guarantees on the cost of paths relative to optimal. Now, as we'll be discussing in this paper, a control set is actually a tuple where the first set is a set of connections, where connections are just start goal pairs, and the second set is a set of trajectories that actually realize these connections. Now, this paper addresses both subproblems. As I hinted at earlier, a lattice is a collection of vertices where each vertex can represent a possible configuration of a mobile robot. Each vertex j induces a connection, which is a tuple from a universal start to that vertex j. Typically, the universal start for us is at the origin. Each connection now, it has a trajectory associated with it, and this trajectory is the trajectory that would actually take a mobile robot from the start to j, to the vertex. And we observe that this trajectory can be applied to other lattice vertices to reach yet further lattice vertices. So for example, here on the right, if j is the vertex 3, 3 pi over 6, that's 3 over on the x-axis, 3 up on the y-axis with a heading of pi over 6, then the trajectory labeled TB that actually would take a mobile robot from the start to j can be applied to other vertices to reach other lattice vertices. The cost of each of these motions would be dependent on the cost of the trajectory and the trajectory you choose. In this slide, we briefly discussed the notion of a control set and a motion primitive. Let B be the set of all possible connections. That is the set of all tuples Sj, where S is the universal start, and J ranges through the entirety of the lattice. Let T be the set of all trajectories. That is the set of all trajectories that realize a connection in the set of all connections. Now, given any subset of connections, given any subset of start goal pairs, we denote TE, the set of all trajectories that are associated with a connection in E. The tuple ETE is called a control set. So a control set is, once again, a tuple where the first set is a set of connections and the second set is a set of trajectories that realize those connections. An element BTB, where B is a connection and TB is a trajectory that realizes that connection, is called a motion primitive. In this slide, we briefly discuss how to take a control set and actually compute a trajectory from start to some vertex j. So let j be any vertex in the lattice, and let ETE be a control set. A path PJE is a sequence of edges that are connections in E. That is, a path PJE is a path whose edges are connections in E. An example is shown on the right. If E is the set SJ1, SJ2, SJ3, then I can form a path from S to J by concatenating these connections. First I use S to J1, then J1 to J4, which is just simply SJ2, and then SJ3, and then SJ2 again to take me from S to J. Now, because each of the edges used in this path is a connection, we know that there is an associated trajectory for each of these edges. So we can form a trajectory from start to vertex j by simply replacing each edge with its associated trajectory. This is shown in yellow on the right. Now, selecting a control set is actually very important, and this is because a control set will dictate not only the quality of the paths that it can generate, but also the runtime that's required to generate those paths. Now, typically, control sets are devised using either heuristic methods or from experience. We observe that if we increase the number of motion primitives in a control set, if we increase the size of a control set, we can increase the quality of paths generated. However, we do so at the expense of a branching factor that occurs during an online search. If we have more options at each step during an online search, we have to check each of those options. It generally takes longer. So there's a trade-off between runtime and path quality. And this observed trade-off motivates the following high-level example. For a set of connections B and a fixed integer k, can we compute a control set whose set of connections is size no more than k and such that the worst case ratio of trajectory costs to optimal is minimized? Now this high-level problem is a problem that motivates the entirety of this paper, and we'll discuss it a bit more formally later on. But in order to do that, we need some way to evaluate a potential control set. And this is what the T error does. Suppose we have a control set E. Suppose we have a set of connections E, and let J be some vertex in the lattice. We say that the cost to J using E, denoted CJE, is the cost of the shortest path from S to J using only edges in E. We define, given a real number T greater or equal to 1 and a control set, we define the T error of the set of connections E as the maximum ratio of costs in E to J to costs in B to J. Now we observe that the cost in C to J is by definition the cost of the shortest path using only edges in E from S to J. And the cost in B to J is the cost of the shortest path using only edges in B from S to J. However, because B is the set of all possible connections, the cost in B to J is the cost of the direct motion from S to J, and therefore is the optimal cost. So the T error is the maximum ratio of costs using only edges in E to direct optimal costs taken over the worst case vertex J. Now this definition allows us to define the minimum case spanning control set problem. Given a set of connections B and the optimal costs to each vertex in the lattice J, in the lattice vertex being J, and a real number k greater or equal to 1, can we find a control set whose set of connections has size no more than k and such that the T error of the set of connections is as small as possible? This problem is very similar to the minimum T-spanning control set problem that was proposed by Pivtoreko and Kelly in 2005, and then reformulated as a mixed integer linear program by Botros and Smith in 2019. Now it should be noted that the mixed integer linear program can be tweaked slightly to solve the minimum case-spanning control set problem as discussed in this paper. Now hitherto we have assumed that the cost of trajectories is known. But if we wish to take into account the preferences of a user, then we need some way to allow the user to judge the cost of paths. We say that a user evaluates the cost of a path PJE, that is a path from S to J using edges only in E, as the linear combination of weights and features of that path. Now the features of this path can be whatever we like. It could be the arc length of the path, the time required to traverse the path, the maximum jerk experienced along the path, the integral of the square jerk along the path, whatever notion of comfort, travel time we like. And W is a set of weights that represent the individual importance of each feature relative to every other feature for a single user. We notice also that a path PJE that is optimal, say, for a user W1 can be evaluated by a user whose weights are W2 as follows. So parsing this a little bit, the cost U EW1 given W2 is read the cost of a path using edges only in E that is optimal for a user whose weights are W1 being evaluated by a user whose weights are W2. And this is given as follows. PJE represents So we take the minimum over all possible paths using E from S to J and weights W1, and we attempt to minimize the cost. Once we find the path that minimizes those costs given W1, we evaluate the features along that path. Then we take the inner product of that with the weight system W2 representing the weights of a second user. With this in mind, we observe that the optimal weight given the optimal cost of a path given weights W is given as UBWW. This is the cost of a path using all possible connections that is optimal for a user whose weights are W, that is then evaluated by a user whose weights are also W. With these definitions in mind, we can formally state the problem that we're solving, that we're attempting to solve in this paper. So, given a tuple BW star, where B is a set of all connections and W star represents the true user weight of a single user, as well as a number K greater or equal to 1, can we find a control set EW, so a set of connections together with a weight such that the set of connections is no larger than K, and that the tuple EW is the minimum argument of this. Let's parse the ratio a little bit. This ratio for a single vertex J is the ratio of the cost of a path from S to J using only edges in a connection set E prime that is chosen to minimize the cost given weights W prime, that is then evaluated by a user whose weights are W star, and we're taking the ratio of that cost to the optimum cost given weights W star to J. We're taking that ratio and we're computing the worst case vertex J for that ratio. And we're trying to determine the minimizing sets E prime and W prime. The problem with the problem statement stated earlier is that it assumes that a true user weight W star is known. This is often not the case. A user may not be able to say what their true user weights are. Moreover, if they provide demonstrations, the demonstrations may not reflect their true optimal user weight. We make the following assumption. We assume that for a single user providing demonstrations D, that user will provide demonstrations D such that the features are normally distributed around the optimal features. This allows us to, provided a set of demonstrations D, we can therefore estimate the true user weight W star using the conditional expectation of the weight given the demonstrations. Now, to attempt to solve this problem, we apply a separation principle. We begin by computing the estimate W hat. That is the conditional expectation of the weights given the demonstrations W. Using this weight structure W hat, we compute costs. We compute optimal costs assuming weight W hat for all trajectories. We then compute a minimum case-spanning control set E hat for the resulting lattice, and we return E hat W hat. That is, we return a minimum case-spanning control set for a lattice whose costs are generated using the weight W hat. Now, because W star is not known, the original problem is unsolvable if W star is not known. We consider two approximations, two estimations, I should say. The first estimation is simply where the value of W star, where the value of the true user weight is replaced with the plug-in estimator W hat. So essentially, the optimal user cost W star is replaced with the a conditional expectation of W given a set of demonstrations. The second estimation we use for the problem is, instead of simply replacing W star with W hat, we take the expected value of the costs. Now in theorem 1.2 of this paper, theorem 1 and 2 of this paper, we actually show that the tuple E hat W hat is a solution to both of these problems. To evaluate our approach, we attempted to capture the essences of three user archetypes. In particular, the lattice we used with which to perform our minimum k-spanning control set separation was a 4x7 lattice, 4x positions, 7y positions, together with 8 headings, cardinal and ordinal, and 3 speed values. This results in 6 different starts and 672 connections for each start. The environment we used, it was a 15 by 15 grid, again with 8 headings and 3 potential speed values, resulting in 5,400 different states. On the right is an example of one of the k-spanning control sets that we were able to generate. Now, as I mentioned earlier, the goal of this evaluation was to demonstrate behavior for 3 different archetypes, to determine whether or not we were able to learn behavior for 3 primary archetypes. The first archetype reflects an aggressive user. This is a user who favors high travel speeds and sharp curves to simply minimize the travel time. The second is a cautious user. A cautious user favors more gradual turns and lower speeds. And finally, a third archetype, which is just a moderate user, who's a combination of the 2 extreme users. Now we obtained 3 demonstrations for random start goal pairs for each of the archetypes. And from that, we were able to estimate weights for each archetype. We ran 40 trials for each value of k in the minimum k-spanning control set. So the 3 values of k we considered were 25, 50, and 100. That reflects 3 different possible branching factors. Now, again, the goal was to see if we were able to learn behaviors similar to those presented here. The 3 archetypes presented here are for one particular map. And just as an example, for these maps, we saw that we could capture the essence of each of these archetypes quite well, which is shown in the bottom 3 figures. As a basis for comparison, we use a naive estimator approach, which is in the naive estimator approach, we don't estimate the user weight W, we choose it randomly, construct a lattice using that user weight to define costs, and then solve the minimum k-spanning control set problem on that lattice. We use this as a basis for comparison, and we see that in the training error, meaning when we directly show trajectories to be learned and calculate the t-errors from those known and observed trajectories, we compare the t-error for the set of connections E learned, which is the minimum k-spanning control set that we learned using weights W hat, to B learned, which is the set of all possible connections using weights W hat, to E naive and B naive. It's the same basic premise, but instead of using weights W hat to define the lattice, we use a random weight. And we notice that, yes, there is a sizable reduction for both of these potential control sets compared to the naive approach. This shows that it is important to try to estimate the user weight W to decrease the t-error. Breaking this up into possible cases of k, meaning the size of the control set, we see that for each value of k considered, 25, 50, and 100, the t-error in all 3 user archetypes is low and decreases as k increases, meaning the larger we allow the control set to be, the smaller the resulting t-error, which is expected. We compare this t-error to planning time speed up. So this is the amount that the planning time is reduced by selecting a set of k elements instead of using the set of all possible connections during an online search. And we see that even using a k value of 100, so a branching factor of 100, we still receive a speed up of around 10 times with a t error of around 1.2 times, so or 1.15. So achieving a t error of only about 15%, we can still speed up the online search by a factor of 10, even using a k value of 100. And obviously, as the k decreases, we receive an increase in speed up for all three user models up to around 35 to 40%, to 40 times. Now we consider the test error. So in this case, we are not assuming that a start goal trajectory is demonstrated. We're selecting a start goal trajectory randomly and comparing the t error and the cost time speed up. Again, we use the naive approach as a baseline. And in this test error, similar to the training error, we see a fairly low, a much lower value of t error compared to the naive approach in both the learned minimum case spanning control set E and the full set B. Similarly, and similar to the training error, if we compare the t error and the planning time speed up for various levels for various k values, 25, 50, and 100, and for all three users, we see a decrease again in the t value as k is allowed to increase, and a decrease in the planning time speed up, so requiring longer time but producing nicer paths. And even when k is 100, so again, even when using 100 as a branching factor, we say a speed up of around 25 times and a t error of around 1.2. So again, with about 20% error, we can speed up the planning time by around 25 times. To summarize, in this paper, we learn a lattice, and we learn, by learning a lattice, we mean we learn the costs of trajectories on that lattice by estimating a weight W that reflects the weight of a user, and we estimate that weight through demonstrations. We then consider a trade-off of path quality and path computation time, and we see following our separation principle of estimating W first and then computing a minimum case spanning control set, we can substantially improve performance while keeping the error quite low. In future, we would like to validate our work using a user study. Here we only did simulations. We would like to do a real world user study. And we'd like to consider different trajectory planners. So in this work, we used only clothoid-based trajectory planners to achieve actual trajectories, tuning the minimum curvature and curvature rate, or sorry, maximum curvature and curvature rate in the planner. We would also like to include situational awareness, and by that we mean perhaps not all lattice vertices are worth considering in all situations. For example, if you're traveling quickly down the highway, then perhaps the configuration of being 1 meter over from the car and with a heading of 180 degrees is not worth T-spanning. It's just not something, it's not a configuration that will arise on a highway. This will, we assume, provide even more speed up in time and reduce the T error yet further. Thank you very much for your time.